Welcome back to Physics through Computational Thinking. Today we are going to talk about damped oscillators, and in this video we'll work out through some examples of damped oscillators. So let's go ahead and get started. For a quick review, we talked about simple harmonic oscillator in second week. This is the equation for simple harmonic oscillator, and its solution can be written in these four different ways, and we plotted some of these styles of solutions, and we saw that all of them represent oscillatory sinusoidal behavior. Let's go ahead and make this equation a little bit more complicated by adding a damping term to that, and to do that we'll take the example of LCR circuit. So we'll take a damped oscillator which is damped by resistance, and this is a very natural example to consider because it's extremely difficult to make a pure LC circuit. All the components that are made out of metals, inductors and capacitors, they come with some amount of resistance, so there's not really a perfect inductor or perfect capacitor. So whenever we build a LC circuit, there's always a small resistance component to that, and that is being represented by this resistance R over here. So we'll take this circuit to be an LCR circuit where pure inductance L, pure capacitance C and resistance R in the circuit. And for LC circuit we saw that the equation was L divided by dt plus Q by C equal to 0 using the Kirchhoff's law of loop. When we add a resistor, the potential drop across the resistor is IR, and adding that terms gives me the equation for the damped oscillator or this LCR circuit is L di by dt plus Q by C plus I by R equal to 0. Now the current I can write as dq by dt. So when I write current as dq by dt, I get this equation over here, and d square q by dt square is now minus q by lc. This is the restoring term, and minus R by L dq by dt, which is the damping term, because dq by dt is like a change of current and it's always in the negative direction, negative to change of current, and therefore this is the term that causes damping. Naturally, when you add a resistor to a circuit, there's Joules heating, and that Joules heating is responsible for losing the energy in the system, and therefore the oscillation amplitude or the charge in the capacitor is going to die down. And that's why we understand this term as a dissipative term or a damping term. So let's go ahead and look at this problem over here. There are 4 or 5 different parts of this problem, and what we'll do is we'll go ahead and solve out these parts and understand how to go about it. So the first question here is identify the time scales in this problem and the role they play. So I've got an equation, I've got a circuit, this equation's got a bunch of time scales. We have to figure out what are the time scales in this problem and what is their importance. Then we have to calculate at what rate do we expect the average energy in the capacitor to reduce. And then third part of the problem is try the solution of the form given below. This is the solution that is given, that we have to try out whether this is an acceptable solution for this differential equation. And often enough, a good way of solving differential equation is using knowing a solution or guessing a solution. And this is what we are trying to do here. We are guessing a solution. We are assuming that the solution is of this form and see if this satisfies the differential equation. In that process, we will fix some of these unknown constants in the problem. Later on, we'll try to solve this as an initial value condition with the initial condition that Q at 0 is 0 and Q dot at 0 is 0, and Q, that is a charge in the capacitor, at 0 is Q naught. And then I think this last question is a repeat of B. At what rate average energy in the capacitor is decreasing, assuming a very small resistance in the circuit. So I think that is just a repeat of this, so we can remove that. Let's go ahead and solve this problem. So we'll go back to the blackboard. The equation that we have got here is d square q by dt square is equal to minus q by lc minus r by l dq by dt. We have to find out what are the time scales in this problem. Now you can read out the natural time scales that are present in the problem using the differential equation itself. Each of the term here has dimensions of q by time square. You see that this term has dimensions of charge by time square, and if this equation is right, then each of these terms have to have the same dimension, and that tells me that LC must have dimensions of time square. And similarly here I see this is one term of time present here, there are two of here, there is q in the numerator, there is another q in the numerator, so one time dimension will cancel out, so I must have that R by L should have dimensions of 1 over time. That's the only way the time will make sense, because LC has dimensions of time square and R by L has dimensions of time. I see that if I multiply LC and R by L, so LC and R by L, if I multiply them together, I get dimensions of time, but this is simply RC. And it's not surprising, we know from RC circuits that RC is the time constant for the RC circuits, and therefore we get three dimensions, three scales in the problem, or three dimensional quantities in the problem that are dimensions of time made up with the constants of the problem. So these what we call as time scales in the problem. So there are three time scales in the problem. We have got first time scale LC, second time scale R by L. Well, LC is not the time scale. The time scale here is square root LC, and the time scale here is L by R. And the third time scale I have here is RC, which is in some sense emergent time scale given the time scale given these first two time scales. So we have got three time scales in the problem. Let's see what these time scales are doing, and for that we have to go back to physics. We have to look at the equation and ask what is each term doing, and we can note from here that this term over here, this is responsible for oscillations, so this must be the primary time scales for oscillations, and clearly resistance is the damping factor. This is the damping term, so L by R must be responsible for damping. It's not evidently clear directly what is RC doing, but it's an emergent time scale. It's a product of oscillation and damping time scale, so it doesn't matter. These are the two important fundamental time scales in the problem, the oscillation time scale and the damping time scale, and they are doing interesting dynamics, and that's what we are going to explore in this problem. Let's go to the next question. It says at what rate do you expect for the average energy in the capacitor to be reducing, and that we can do that estimation based on the dimensional analysis that we have done over here. Let's go ahead and think about that. So I want to find what is dE over dt. To estimate that, I can use dimensional analysis, and dimensional analysis simply says that numerator is dimensions of energy, so we can simply go ahead and estimate dimensions of energy. So energy in the capacitor is given by q square by 2c, so that's an estimation. I can write the energy scale as q square by 2c, but q itself is given by q0, which is the initial charge in the capacitor, so we can estimate approximately energy is of the order of q naught square by 2c, and time, there are various different time scales present here. Question is which time scale to choose, and we might be tempted to say that let's choose the damping time scale L by R, because the time responsible for damping is L by R. So let's go ahead and put that time scale over here, and that gives us an estimate for dE by dt, or the rate at which energy is changing in the capacitor. That's one estimate, and this approximately evaluates out to q naught square. The constants are not important, so we get q naught square R over LC. Alright, let's go ahead and look at another way of thinking about the same problem, and for that I'll make some space here. I'll erase this part, and let's go ahead and think of another way of doing this problem, and I can say dE by dt can be estimated by, especially when the capacitor, when the resistance is very small, Joule heating is very small, damping is very slow, I can say that d by dt is delta E over delta T, where delta E is rate at which energy is changing. So in one cycle, our energy lost in one cycle, and in one cycle, because of Joule's heating, we know the energy lost is IR square, is of the order of IR square, and the time taken for that is the oscillation time period, which is of the order of square root LC. And now we can go ahead and put in units for I. I is current, so it's again current over time. So current is Q naught, charge is current is charge over time, charge is Q naught, time is square root LC. So I get another square root of LC factor, and that squares up because I already have one square root LC factor, and resistance squared. So that gives me Q naught R square by LC. I think oh sorry, this is Joule is not IR square, it is I square R. So let me go ahead and correct that. So let me go ahead and correct that. Joule heating is I square R by delta T, which is square root of LC, and I get I square is Q naught by square root LC square, and I get actually the power is I square R, so I have to multiply delta E. Delta E is Joule heating, which is I square times the time delta T, which is again of the order of oscillation time period. So I square is Q naught by square root LC whole square times R by square root LC times delta T, which is of the order of square root LC. So as a consequence, I get here Q naught square R by LC. Interesting thing is that by both logic, we found the same result. So the naive dimensional analysis over here gave us d by dt simply based on dimensional analysis gave us Q naught square R by LC, and when we took into account physical input that damping is happening because of Joule heating, Joule heating is I square R. If it happens for a time period, for one time period of oscillation, that is delta T, and that delta T is given by square root LC, and this is same as this delta T, which is square root LC. As a consequence, we got substituting all of that and estimating current as Q naught over the oscillation time period, because Q naught of the charge is going out of the capacitor over oscillation time period. We estimate current as Q naught over square root LC, and putting it all together, we get the same result. So physical input and naive dimensional analysis using simply dimensions of energy and time gave us the same result. So what we learned from here is dimensional analysis is a very powerful tool. Sometimes we can get fantastically accurate results by simply doing dimensional analysis. Let's go ahead and look at the next part of the problem, which says that try this form of the solution and see if this works out as a solution for this differential equation. So let's go ahead and try that out, and the form of the solution that we want to try out is Q of t is equal to a e to the power minus alpha t cosine of beta t plus phi. And in order to do this, I will need to find out what is q prime of t or q dot of t, which is a, taking derivative the first time, I get minus alpha e to the power minus alpha t cosine of beta t plus phi, and taking the derivative of the cosine term, I get a e to the power minus alpha t. Derivative of cosine is minus sine, so I get minus beta sine of beta t plus phi. So that's q prime, and I also need q double prime of t. So for that I'm going to take q prime of t and take one more differentiation, and that's going to give me a, again when I differentiate with respect to alpha, I get minus alpha square and e to the power minus alpha t cosine of beta t plus phi. Taking the derivative of the cosine term gives me minus beta, so I get a times minus alpha minus beta e to the power minus alpha t sine of beta t plus phi. Coming over to the second term over here, coming over to this second term, I get plus a, taking the derivative to alpha, I get minus alpha minus beta e to the power minus alpha t sine of beta t plus phi, and taking the derivative of the sine, I get a e to the power minus alpha t. I get derivative of sine is cosine, and I get beta out, so it's minus beta square, and I get cosine of beta t plus phi back. So that's q prime of t and q double prime of t. Let me go ahead and clean up, and to clean up, what I'll do is I will go ahead and write q prime of t as a e to the power minus alpha t, and in the brackets I can write minus alpha cosine of beta t plus phi and minus beta sine of beta t plus phi. And again, collecting terms in q double prime of t, a e to the power minus alpha t comes out. I get two sets of term. One is cosine of beta t plus phi, and that is multiplying minus alpha square and minus beta square, so I can get rid of that. And sine beta t plus phi term is multiplying minus alpha beta twice, so I can get rid of that also. So the cosine term comes with minus alpha square minus beta square cosine of beta t plus phi, and sine terms comes with minus 2 alpha beta sine of beta t plus phi. Now I can go ahead and get rid of this stuff. Now what I want to do is I want to look at the differential equation. So that's my q of t. Let me write down my differential equation. Differential equation was q prime of t is minus q by LC and minus q by LC minus r by L dq by dt. So let's go ahead and substitute q prime, dq by dt and q in this equation, and compare on both sides the coefficients of sine and cosine terms. And so if I look through all of that and compare coefficients of cosine term from q double prime of t, I get minus alpha square minus beta square from q prime of t, which is over here, times e to the power minus alpha t, which is going to cancel out. So rather it's coefficient of e to the power minus alpha t times cosine, which is linearly independent from e to the power minus alpha t times sine. So comparing the coefficient, I get from the left hand side minus alpha square plus beta square, and that must be equal to the right hand side, which is minus q by LC. From q I get the cosine coefficient as simply 1, that's multiplied by 1 over LC, so I get that. And from dq by dt I've got a cosine term over here whose coefficient is minus alpha, so I get minus plus r by L times alpha. That's my equation 1. And comparing coefficients of sine, I get from the left hand side q double prime is the coefficient of sine, I get minus 2 alpha beta, and that's multiplying a times e to the power minus alpha t times sine. Coefficient of that is this, and over here on the right hand side I got minus q by LC, which does not have a sine term, it only has a cosine term, so we don't get any contribution from there. But from dq by dt we've got a sine term, so I get minus r by L times minus beta, so it becomes plus beta, and that is equal to, so is the equal to, let me put that back in. So this is the left hand side. The right hand side, the first term gives me no contribution, the second term gives me minus r by L times minus beta, so that becomes plus, gives r by L times beta. So this is equation number 2. Now solving 1 and 2, we get from 2 we get 2 solutions. Equation 2 gives me 2 solutions. It gives me either beta equal to 0 or alpha equals minus r by 2L. I think there's a sign mistake. I should get alpha equal to plus r by 2L. So there's a small mistake here. This should have been a plus sign. This should have been a plus sign. So now from equation 2 we get 2 solutions, either beta is 0 or alpha is r by 2L. Now beta equal to 0 means that this term becomes simply a constant cosine of phi, which can be absorbed inside A. Therefore this term is meaningless, and the solution is only e to the power minus alpha t, which simply means that it's an exponentially decaying kind of solution. And that is a solution without any oscillation, and this is called the overdamped case. So beta equal to 0 gives me overdamped oscillators, and when that happens, the first equation gives me the value of alpha. So for overdamped oscillators I get beta is 0, so I get minus alpha square equals minus 1 over LC plus r by L alpha, which is a quadratic equation you can solve. You'll get 2 values of alpha, so there are 2 decay rates, 2 exponential decay rates for 2 different branches of alpha, and our general solution will be a linear combination of those 2. I will leave that for you to figure out. Let's go ahead and talk about the other case where you get this branch of solution, and this corresponds to underdamped oscillators. And for this case I can go ahead and substitute alpha equal to r by 2L inside the first equation, and when I solve for beta, I'm going to get make some space for that. So for underdamped I'm going to get beta equal to square root of 1 by LC minus r square by 4L square. Therefore what I see is that this equation provides me a solution for my differential equation and it gives me more than one branch of solution. It gives me a branch of solution when I've got beta is 0, that means no oscillation, just exponential decay. Then I've got underdamped oscillator where alpha is non-zero and beta is non-zero, and I've also got a third more which is called critically damped, and that happens when I get exactly this term to vanish.